Okay, so why don't we get started today? So welcome everyone to Lynchburg's colloquium. Today we're honored to have Professor Goff here from Lynchburg College. Professor Goff got his Bachelor of Science degree at Vanderbilt University and then master's and PhD at Indiana, where he worked on photon tracking. He's been a visiting professor at Kenyon and Oberlin College, and he came to Lynchburg College in Virginia in 2002. He's been the chair since 2003. Is that right? Professor Goff is an expert on the physics of sports and is the author of a great textbook that's called Gold Medal Physics that we use here at UVM. So it's a pleasure to have him today talking about Tour de France and soccer ball aerodynamics. And just before we start, a small token of our appreciation for visiting here.
I just want to put it in. So, first day in Vermont, very impressed with this place. Does everybody think it's nice and cold today? Do you like that? I love it. I think it's great. You have some pretty nice views out your faculty windows too. So, physics of sports is not perhaps the traditional research area that a lot of people going into physics think about. In fact, there's a big engineering community that probably dwarfs those in physics who do sports science. The interest that I got into sports physics was high school age, thinking I'm going to be a professional baseball player. And I mentioned to a few faculty members that I joke around, I'm one of those few people that went to physics because something else was too hard. I found hitting a curveball to be a little more challenging than diagonalizing a matrix in a quantum mechanics class. That was a piece of cake. So I always had an interest in sports, and then once I got to a small liberal arts college with very few faculty members, I found that not everybody wants to do the kind of things I was doing in my graduate school days. They would want to do things in sports. They were athletes and they played sports and were majoring in physics. And this niche just kind of started snowballing, and it's just been a lot of fun. I got involved in Tour de France modeling 10 years ago, and the soccer modeling took place about half that time ago, about 5 years ago. And just curious, how many people follow the Tour de France? Just curious. Oh, and you all just sit together, right? So this is the soccer side, is it? So how many are World Cup soccer fans? So it's smattering on both sides. Okay, I love the statistics. Let's do it. So I'm going to try to split this talk into two pieces just to give you a flavor of the kind of research that I'm doing. How many of you here on athletic teams at University of Vermont? How many catamount athletes? A couple here. What sports?
Cycling.
Oh, very nice. We should talk afterwards. I'm curious to know your thoughts on what I have to say. Siena last night, right?
Yeah. Basketball.
Just checking to see. There's a lot of games on in the restaurant level, so got a flavor of a lot of things local. Here's the idea that we had 10 years ago. The Tour de France website every year will show you the stage profiles for all the stages. This is run 3 weeks in July. There are 21 stages. Sometimes the first one is a stage 0, sometimes it's stage 1, but it's a very short prologue, we'll call it. A couple of time trials, and it's just beautiful scenery. Maybe you start in Corsica, maybe you start in Belgium, but most of this is run in France. And you get a profile like this, and if you've ever watched the Tour de France, I don't think you'll agree that the actual terrain looks like this. This is just a very rough sketch that we get. On the horizontal here, we see distances in kilometers. These are actually distances biked. They're not actually showing you horizontal projections of these distances. And then you get these elevations here in meters with different mountains labeled here. The Alpe d'Huez is the very famous 21 hairpin climb up the mountain that they actually did twice this year to celebrate the centennial of the Tour de France. And these mountains are classified. The unclassifiable, the big climbs, are these HCs. Your French might be better than mine. I'm not going to try it. So the Ors category, however it's pronounced, climbs are the really fun ones to watch, and you got fans everywhere. And we were trying to find some way of actually predicting the Tour de France ahead of time and see if we could come up with the stage winning times. But this is all we've got, and crashes happen, high winds happen, rains happen. We also learned that they find ways of using the restroom, perhaps while they're still on the bike. They eat, they do all kinds of things on the bicycle. Fans are dressed up like clowns or super action heroes and running along with flags, and it's a challenging thing to model. This is also a 2D profile, and of course the race is not run in 2D. But the limited number of points we get here can actually be supplemented with some Google Earth websites and some other websites where you can go in and follow the terrain. So, for example, maybe we'd like to know what's going on in here, and the Tour de France website doesn't give us any information about elevation here or how far that slope is down to that little crotch right there before you get up to the top of that peak. So we would go to some other websites to fill in some of these gaps. How many of you are in the intro physics course here? Or taken the intro physics course? Did you ever wonder when in the world are we ever going to use the inclined plane? Well, we said, you're giving us heights and distances, let's make inclined planes of all these things. So we learned to solve the inclined plane in Physics 1 or high school, whenever you first met this. So we see we've got a weight on the cyclist. There's some resistive force here that would be coming from air resistance and rolling resistance. The road is pushing the tires forward. We can model this as kind of a force that originates from the cyclist power output, normal force from the road, and Physics 1, right? Just break these things into various components. It really is just a one-dimensional problem. We can set this thing up on a computer in 2 dimensions and have these things kind of make some nice pictures, but it really is just a one-dimensional problem here. And you can solve these second law equations for Newton analytically. Now, this is a simplification. I mean, anybody who's going to get into modeling knows that this is not 21 hairpin turns and someone urinating on a bicycle. I mean, this is a challenging thing to model here. So we thought we would give this a shot. We looked online at some, I'll get to the parameters in a moment. I think everyone's probably seen these forces before. So you've got the weight, you got the normal force. We model the biker's power output divided by the speed of the bike like so. There's a lower limit cutoff if the speed gets too small here. The retarding forces, you got a lot of drag force. So what speeds can you cycle in your bicycle? I'm just curious.
If I'm going on a flat for a while, I can probably maintain about 26, 27 miles an hour.
Yeah. So think about that. Get upwards of 30 miles an hour, stick your hand out the window. I mean, there's a hefty amount of air resistance there. If you're going slowly, you're fighting a lot of resistance with the ground. This is the rolling friction, deformation of the tires. You lose some energy there. So kind of this ancient Coulombic model of friction we use to model the rolling friction here. And we've got these two resistive forces here, the drag and the rolling resistance. We lump into a single retarding force. The biker outputs some power, and of course the earth is interacting with the bicycle as well. Some numbers. We just found the average cyclist mass. The bicycle has a mass lower limit, and 77 kilograms seem to work for an average of all the elite cyclists that are competing. Lots of research has been done on the tires, rolling resistance, air density. I'll talk about improvement to this in a little while. When we first did this, we thought, well, we're going to have to come up with some kind of drag in an area. Usually these things are measured together. They're very hard to separate. Had a student try to take a picture of himself on a bike with a grid and try to actually work out his area. But it's hard. I mean, the elbows are moving out. Try to get some average value. So we found some wind tunnel data. And at the beginning, we just split this up into 2 regions. If you're going uphill, if you've ever ridden a bicycle uphill, you tend to be more upright on the bike and you're really fighting to get up the hill. If you're going downhill, you're really crouched and you're sleek and you love the feel of the wind in your face, and you're trying to keep the air resistance down though. So we reduced the air drag going downhill. Theta was our inclined plane angle, remember? So we made some modifications in this past year. We actually then used an exponential model for the atmosphere to give something more realistic to the air density. They're climbing mountains that are 2 kilometers above sea level, so we want to include the little reductions in the air density. And we then introduced a continuous model for this, still consistent with what people were measuring in wind tunnels. And I was trying to think, is there something out there that's kind of constant over here and constant over here and just kind of joins those 2 flat lines? And having just taught magnetism, I thought, well, let's try a hyperbolic tangent function. I don't think it's too terribly sophisticated. Whatever you pick for the function here is going to make too much difference. You just need something that's kind of one size here, and then you need to join these 2. But this gave us some parameters we could play with. And it gave us 4 parameters here for the drag coefficient times the cross-sectional area of the cyclist. And I'll come back to how we find these in a moment. With the power output, lots of physiological studies, lots of cyclists going bicycles with oxygen masks, and scientists in lab coats and clipboards sitting there, the commercials you see. And they're doing all kinds of experiments to see what kind of power output you can get. Now, when you're going downhill, you're fighting a lot of air resistance. You're flying at, as you're saying, you're well up close to 30 miles an hour, something downhill. Putting more power into it is not going to help you that much. You're fighting a v squared here in the drag. So it's not, the model's not too sensitive to this number. This right here is enormous, but it's only over a really tiny stretch where there's a very steep incline. And I'll show you why these goofy numbers will pick in a moment. But then we tried to find something more kind of, this main is where we're going to have most of the power, and then another transition region. Again, trying to stay consistent with what experimenters tell us here. Well, this past year we introduced a continuous model, and I found that if we go out to just a 3rd order polynomial on the angle here, we could get pretty good matching with the 2012 result that we had. We tried many different things here. We tried higher order polynomials, we tried various functions. We're basically trying to come up with some idea of, if we have a steep hill, we need a lot of power. If we have a very steep hill that's going down, we don't have that much power at all. And trying to find something that matches the experimental data. So 4 more parameters. We have 8. So we have an 8-dimensional parameter space we can line here. So here's what happens. In 2012, we had 441 angles for the 21 stages. So 441 inclined planes in a row. And we found that there were cutoffs. There are these gaps here. There's another one there if we wanted to even introduce another cutoff. We found a gap here. We found a gap just right underneath that point that sits right there. And this is where we were using these discrete models. So we have 6 angles here. Most of them are in this kind of lower or main region here. And it's worked well for 10 years. We were predicting quite well, as I'll show you in a moment. That almost looks like you could make a 3rd order polynomial out of that picture. Now, we had to make some modifications because there are some stages that aren't as long as other stages. So the prologues, the team time trials, the individual time trials, you're allowed to do drafting in a team time trial. If you're ever watching, the lead cyclist is doing all the work and the buddies are back there taking it easy, and then they'll swap in and out. Can't do that on the individual time trials. We'll get back to Tony Martin here, but the clothing is very aerodynamic. You have this nice teardrop shaped helmet. You're crouched forward. These bikes almost have no handlebars you would recognize if you've never been a cyclist. You close off the spokes back here, the shoes are basically attached to the pedals, and I mean, as much aerodynamic help as you can get here to make for a very fast ride. So we found over the years that if we take our drag coefficient times the area, this drag area parameter, we drop it by about 20%. That seemed to work pretty well from what people were finding in wind tunnels for normal cycling. We did have to make that modification. So here's what happens. 2011, the first time I decided I would put this on a blog. And I thought, well, I'm going to stick my neck out, so instead of publishing it, which is what I've been doing in the past after the race was done, trying to get people to believe, yes, these were actually, this predictions were this good before the race started, I started putting them online on my blog, and we were getting some nice agreement here. Just nice is a relative term, but here's 2012, so there's Bradley Wiggins, who had a pretty darn good year in 2012, and we look at the Olympics too. So here's the actual winning result. We're always after the winner. We're not trying to predict one specific bicyclist here. And we were off by 22 seconds, which for a 7-minute race is about 5%. And the first time we did this, we were only off one stage by 10%, and then we just kept getting better and better and better. I think maybe this one here was nearly 4 hours that we were off 7 seconds. I was kind of yelling in my office when that time came in. The next day we were 18 seconds off. And, you know, we kind of thought, well, gosh, we'd like to get better than 10%. Now that we've done this a while, let's get better than 7% and see how many we can get kind of under 2% or so. The overall time, we've always done really well. We're off 16 and a half minutes in 2012, just to 30%. If you add up these errors in quadrature, I think it's around 29% or something, so closer to a percent if you weight them a little bit differently. You got rest days in here. These are medium mountain stages, flat stages. So different types of stages that they run. Pure mountain stages are labeled at the end. And the blog statistics go through the roof during this race. And I'm not even going to be too naive to know why. People are betting. And I got contacted this year when the predictions were not put in until the 11th hour. People in Belgium and France and Germany and all over the world are coming, are you going to put predictions on? Are you going to put predictions? Yeah, I'm going to put predictions on. Please gamble safely and all that kind of stuff. So we were ecstatic in 2012, and we thought, well, we're going to use this as our blueprint for 2013. We make this transition to more continuous models. Well, we're going to spend a little time talking about the 2013 race because it had some eyebrow raising moments. But what we did was we used 2012 because we know the answer. We're going to mine our 8-dimensional parameter space. We're going to find those 8 parameters that even make 2012 better than what we had predicted before. And we reduced that overall error 0.32% down to 0.25%. The largest error that was around 7.3% went down to about 6%. So we were able to reduce these things incrementally. If you stared at the picture long enough, you could see a little reduction. And this took several weeks doing this on the computer because, you know, we weren't even sure what functions we were going to make use of at this point.
Sorry, so all the slopes is only available in advance?
The what?
All this, the angles.
Yes. And once the routes are published, then people like me just hide in the office for a week. I mean, that's the hardest part about all of this is just entering all these bloody data points in, for all these different angles. And then, we look at the profiles and things. We don't have that little part there, so we go on a map and satellite pictures and look at these and get more data points. Google Earth is really helpful for this too. But yeah, you get all this data, and when this stuff is presented, the cyclists are sitting in the audience watching, the contadors and the other, mountain climbers and stuff. They see these big mouth. Yeah, that's where I'm going to win and stuff. So they get pretty excited by these pictures. So here's what happened. Now, first day comes along. We have this kind of traditional flat stage. It's about a 5-hour prediction we have. We got under 1%. We're really happy. Log hits are going through the roof. Wow, they're hitting it again. They're really nailing this thing. You know, we're under 4%, under 1%. There's a 6-second difference. Then things started to happen in the second week. And that's what we're going to talk about a little bit here. In fact, if you see a plus sign on that percent difference, it means we're too slow. If you see a minus sign, it means we were a little too fast. So Chris Froome, another UK victory here in 2013.
Question on that.
Yes?
You've got 2 rest days marked. Do you have anything in your model that says after a day of rest the cyclist will be able to X or Y? Or?
Well, when we did this before, the thing is we're going from a day of rest to a pure mountain stage, both of these times. So we're not anticipating some drastic increase in power output, but here I think we had a pure mountain, a flat stage. So no, I mean the only thing we're assuming with the rest days is that they're getting back up to the elite level that we think our model is trying to model. If those days aren't there, then we would anticipate we're just going to be too fast throughout the race. But we got to the end here and we were 2.5 hours off. This is, I don't look at a 3% error and think that's good. I mean, I look at 2.5 hours and think, wow, that's something really happened here. And it's really the second week. And I'll talk about a couple of these stages and what happened. The time trial, we first got a hint at this time trial. The Australian team had an average of 57, almost 58 kilometers an hour. This is almost 36 miles an hour. That's hauling butt on a bicycle. That's really fast on a bicycle. So we started to get curious by how fast these cyclists were going here. We can't predict the weather. We were way too fast on this. They fought terrible weather on this flat stage 10. 30-kilometer crosswinds. A nice thing when you follow this online, they'll show you the direction of the wind. Almost exclusively headwinds. Now, were we too slow? We might have been worried. So, I mean, I take this with a grain of salt. I mean, I'm not going to be able to predict the weather. I have much nicer clothes than I could. So, Tony Martin. I showed you a picture of him winning that stage 11 time trial. He and Chris Froome was right behind him. They were 1 and 2. He won this 54.27 kilometers an hour. That's almost 34 kilometers an hour individual. So there's no team help here. There's no drafting or anything like that. I look back and I try to find comparable stages in the past. He won a stage that was a comparable distance in 2011, a little less than 46 kilometers an hour. And we're just seeing these speeds and just completely baffled by what is going on. We get down to here. This is Marcel Kittel. He beat every single flat stage average winner from 2012 except one. And the one he didn't beat is going to appear here in a moment. The other thing that's goofy about this stage now, this 13 or 12 flat stage, every single cyclist who came in beat our prediction. We're always trying to predict the winner. Every one of them who, we're talking about 170 or so cyclists, beat our prediction. This is 218 kilometers they're biking this day. Very long stage and incredibly large speed. Another one, 173 kilometer stage 13 that's flat here. This is more than 29 mile an hour average. Mark Cavendish beat every single flat stage from 2012. Beat them all. He was the one who Cattell could not beat in the previous one I showed you. The one here, I like this one. 181 cyclists competed this day. They all beat us. 191 kilometer stage. He also, not only did all of them beat us, the person who finished last in this stage beat the winner's average speed in every single medium mountain stage from the previous year. And you go up here to stages 2 and 3 that are medium mountain stages, that average speed from the last place finisher, the person who was the 181st cyclist to cross the line that day, had a better average speed than the winner of the previous stage 2 and 3 that year. And again, we had not seen strategies like this before. We had not, just could not understand this. This one here, just completely crazy. We were 41 and a half minutes too slow. I will come back to this in a moment. Here's a picture of stage 15. Now, I was chomping at the bit for this stage. I mean, imagine this. You're on a bicycle for 221 kilometers. You got a couple of these little category 4 and 3 climbs. You know, not too bad for these professional cyclists. 221 kilometers. You're on this bicycle. You get to that point. This stage 15 is 30 kilometers longer than the day's stage you just ran the previous day. It is also longer than every other stage in that year's race, but 2 of them. Okay? This being one of them. The lead cyclists were at 47 kilometers an hour at this point. Completely baffling how that speed could be so large. And they had this unclassifiable climb to go. So they had completely gotten to this point well in excess of everything that you'd ever seen historically for what people could do in 221 kilometers. And what's the strategy? Oh wait, we still have this uncategorized climb to do. You're straight up a mountain. And all but one of our 181 cyclists beat us. So Chris Froome finished this as the winner. This pretty much sealed the Tour de France for him. A little less than 42 kilometer per hour average. Almost 26 miles an hour here. Unbelievably fast. Here's another one where the weather, this was actually painful to watch, this time trial. They were coming off of these platforms. Hail was falling, rain, swirling winds, and we were too fast, so I kind of write these off as, we publish them ahead of time, but that's just what happens with the weather. I'm going to show you why I thought we would be a little fast. This stage 19 was a little famous for one particular reason. You'll see in a moment. Show you a picture of that. So they don't run the same race every year, which is what makes modeling this so much fun. I had to go back to 2004 and stage 17 to compare to this past year's stage 19 that I was talking about. They have the same starting point, almost the same elevation. Same ending point, almost the same elevation. The same mountains here. They got the same mountains here. I think the only main difference was there was a little sprint area here that was back a little bit farther here. The distance is exactly the same. I mean, you're not going to find 2 Tour de France stages more similar than these 2 right here. Rui Costa from Portugal is the one who won it this past year. 46 of the 170 cyclists that ran like this stage beat us, about 27%. Who do you think won this one? 2004. He did that 6 hours, 11 minutes, and 52 seconds. And Costa came in under 6 hours. Now, by this time in the race, our eyebrows are in the back of our head. I mean, we're just trying to think, what is going on here? That's actually Lance's winning pose for 2004 stage 17. Remarkably similar to Costa. So, we were trying to figure out what the world's going on. Now, so I had this idea when the race ended. First week's okay, second week these crazy speeds, and then you start reading and people are starting to ask the same questions. We're asking, and I would certainly never make a conjecture in a public or even private forum without data and evidence. I'm a scientist, I'm not a politician. So I will not make any claims at all of why I think these speeds are high, because I don't have any, I don't have blood samples, I don't have data or anything like that to come up with this. But I wanted to know, if you went back in history and you looked at the average speed for the winner of the past several Tour de France's, how would that person have fared this past year's Tour de France? All the stars have been vacated. All of Lance Armstrong's 7 straight titles are gone. Floyd Landis's is gone. Contador had to give his 2010 title to Andy Schleck. This is how they would have finished. A 1999 Armstrong would have come in 18th. Last year's Bradley Wiggins would have been lumbering in at 35th place. Cadell Evans from Australia would have been 42nd. Here's Contador. Now, I did put the distances on here for the following reason. Only 2 of these are shorter than last year's race. Last year's race was 3,404 kilometers. So you have these 2 here that were actually shorter. So I would expect a longer race to have maybe a slightly lower average speed. But, 3,430 over 3 weeks, 3,404, we're not talking about a huge difference here, and still finishing well out of the money here, well out of the pictures in the Arc de Triomphe.
Excuse me?
Yes?
Are you taking their average speed and using the distance of the 2013
Yes.
race and then just
Yep,
replacing it?
that's what I'm doing. Very, very, very simple. I'm not trying to weight it or do anything crazy like that. I'm just saying, hey, if this was the average speed you won with that year, where would that average speed have gotten you in 2013? So just, I don't know, notice where the ones are. But I honestly don't know the answer to this question. I've been researching, I've been talking to my colleagues in Europe. I can't find a major technological advance or training advance from 2012 to 2013 that would make that kind of change in the speeds. Now, of course, every Tour de France is different. I mean, I take this with a modicum of salt here, but the point is a lot of people, a lot of publications were writing stories at the time this past July that something looks a little out of whack here. If you got some ideas, I'd be interested to hear from the cyclists in the audience. If you've heard anything new about the technologies, but again, the colleagues I've got overseas who do cycling a little bit more fervently than I do, just as baffled.
I have a question.
Yes.
So you segued to just comparing average velocities, but I wonder, did you apply both models to 2013 to see how each model fared?
Sure. The old discrete model we used was just as slow. I mean, we were just trying to find a way to make this thing a little more portable from one year to the next, so we didn't have to look at all the gaps in the picture. But yeah, I mean, we still noticed that our model was behind what the cyclists were doing. But I mean, this has been working well for us for a decade, and then this past year was a curiosity. And that's what makes science fun. You get a curiosity every now and then. More reading. So we got some publications on this. This recent work has been accepted by the Journal of Science, Engineering, and Technology. I am on the cover of my book. It's just it's the back cover. That's not; those aren't my abs. But the blog here contains our predictions in July, so every day, the day before each stage is run, we do this, and I get a kick out of the hits that I get and the countries I get. But I do want to segue into soccer here. So, second half of the talk, I'll tell you about some work we've been doing connected to World Cup soccer. So, please, if you've got questions about Tour de France, I'm happy to take them in the Q&A, but let me introduce you to some of the soccer stuff. So why do people care? Well, every 4 years, the world plays a sport that those of us in the U.S. think isn't that big a deal. And we don't make up the majority of the world's population. But when I've lectured in England and I've held up one of these balls and I say, okay, I'm going to talk about a soccer ball today, I get, ooh, whoa, it's not soccer anymore. It's football. So, there's a language and a passion that a lot of us in this country didn't grow up with. But 2002, Korea and Japan shared the World Cup, and Adidas is the maker of the ball, and they put out this 32 panels, kind of traditional 12-10 Pentagon hexagon split here, where you've got a pattern of the ball that, if you've ever kicked a soccer ball, you probably had as a kid. Black and white pattern you see down here. The real change came in 2006. When Germany hosted the World Cup, they used what was called the Teamgeist ball. And the Teamgeist ball was the first one that had thermally bonded panels. No more stitching. These are much better technology, keeps the ball even drier inside. And they went from having 32 panels to just 14. And the players started to notice a difference in the aerodynamics. And those of us who studied a little bit about aerodynamics know if you start changing the surface character of an object that's passing through the air, things can change. Well, 2010 comes along, and the Jabalani ball was introduced for South Africa. And it only had 8 panels. I mean, we're trying to get to this perfect sphere ideal with as few seams as possible. Thermally bonded as well, improved bladder design. Because you kept going from something that had lots of places of roughness to something that kept getting smoother and smoother, imagine hitting a golf ball without dimples. Imagine the days in the aristocracy when the golf was just invented, and they're hitting these nice smooth balls, and then the poor bourgeoisie, they get the rough and used balls, are driving them farther. Wait, what? We can't let that happen. So what do you do in golf? You now dimple the whole thing to pieces, and you make it as rough as you can. And it goes farther. It's got less drag on it. Well, they had to intentionally roughen the surface of this ball. Over this whole thing are these little grooves that stick out. They could not have this ball be smooth with just 8 panels. It just changes the aerodynamics completely. So they artificially put fake roughness on there. It's not due to stitching or anything. So in next year, the World Cup comes along, and it's down in Brazil, and the Brazuca ball is the name, but Adidas has not revealed the pattern of the ball. We don't know how many patterns are on this roughness and stuff. The 6th of December is the date when the final World Cup draw is announced, and usually that's the day when the ball is revealed. So I expect to get a phone call probably at that time getting, what do you think of the new ball? Lots of calls in 2012. What's going on with the, or 2010, I mean the Jabalani ball. Why is this thing acting like it's acting? So I'm really anxious to see what this ball is going to look like. So let me just tell you about some of the work that I've done with a colleague at the University of Sheffield. He's got a wind tunnel. It's a small one. They have to use a small prototype ball. There are some larger wind tunnels where you can use actual size balls. There's one colleague I've got in Japan. He's got a really nice wind tunnel you can put an entire ball in. The problem is there's this pesky thing called gravity. where if you hold something and you let go of it, it falls. And you can't put the ball in there with nothing holding it. And you blow air over this thing, it'll either blow away or it'll fall. So you have to jam a big rod in it and hold it there. Well, the thing is, you don't play soccer or football with a big rod shoved into the ball. So I was trying to think, how are we going to analyze a soccer ball, get trajectory information, get aerodynamic coefficients, kind of in its natural environment without having a rod shoved inside of it. So we made use of a kind of a homemade ball launching machine. They've got these 4 counter-rotating wheels, so we can send this thing out with no spin, we can send it out with side spin, top spin, back spin, whatever we want. Angled spin. There's a camera set up here that we use. This is a high-speed 2,000 frame per second camera. We get the information at the launch here. I'm jealous that my colleague took this picture and got the ball coming out. The axes that we set up, we also noted where the range the ball when it landed. We've got a second camera set up back here to try to get the main apex of the trajectory. And this is what some of these pictures look like. So from the launch, we were able to get data like so, and then over the apex, get more points like that. So we've got these 2 cameras set up, and we're going to extract these aerodynamic coefficients from them. So how do we do this? Well, good mechanics course, you set up the second law. You got the weight of the ball here. It's nearly a pound, more than 4 newtons. So if the ball has a certain spin, in this case it would have some back spin. You kind of kicked under the ball and it's rotating like so. There's a force we call lift, sometimes called a magnet force. Goes by various names. There's kind of back people doing aircraft flight dynamics and stuff. It's kind of antiquated, but we still call this a lift force. But the idea is the air that gets whooshed around like so will get pushed down a little bit more, so it separates off the back of this ball asymmetrically. It's like you look out the back of a boat and there's a rudder there, and you want to turn the boat, you turn the rudder, the water gets pushed one way, and good old Newton's third law says, well, the boat's got to go the other way. So if you can make the water separate asymmetrically, one side or the other, you can make the boat turn. It's the same idea here. You push the air back, not straight back, but off to the side, and you get this lift force. And then, of course, you got this drag. Now, the air just exerts a force on the ball. You know, it's we nerdy scientists that come along and want to break it up into these different components and give them names and stuff like that. But, I mean, you know, the air is just, you've got a buoyant force on it. But we set up this equation. We could even have a little side spin if there was a component to the spin. Also, out of this plane, the spin axis here would be coming out. If we rotated that in any direction, we could include all 3 different pieces of this full 3-dimensional problem. And here's what we do. We solve Newton's second law using all those forces. Have to do this numerically, but we don't have coefficients to put in. We don't have a drag coefficient. We don't have a lift coefficient to put in. So what I have to do is I have to do an optimization here. I have to try to find what coefficients are going to give me the solution that sits right on those data. And that's what I'm showing you here. Here's camera 1 data, here's camera 2 data, and the solid curve here is a pure numerical solution to the second law. And I optimize it so that I can get camera 1 nice and fit right there, nicely squares fitting, camera 2's data. And I also look at the Reynolds number, which is proportional to the speed of the ball, to see if we're in a certain domain where the drag coefficient might change. And we happen to make sure that this entire trajectory is at a Reynolds number bigger than 2 times 10 to the 5. And I'll show you why that's important. Yep.
Is your camera tracking the spin of the ball as it goes through? Like, do you know this is a no-spin run, or is that based on your...
We set it up for no spin, and I can show the spin. I mean, it's taking plenty of frames per second, 1,000 or 2,000 frames, depending on which one we're doing. But so yeah, we can track the spin. I'll show you the spin results in a moment. But what I do is I look at the range. Now, this particular ball went 21.9 meters, as a matter of fact. And I can show you how sensitive it is to change a non-spinning, so a ball with no lift. You change its drag coefficient from vacuum, which is going to land out here a little 26 meters or so, 25.5 meters, all the way out to a half, so 18.3 meters. Well, our ball landed right here. Well, not only did we match the range exactly, the 3-digit accuracy, I should say, our camera data also fits. That one's a little bit of a fudge because they all kind of go on that one. But our camera 2 data fits right on that curve with CD is 0.2. Now, one problem, I'll show you the experimental versus computational over experimental squared. Has a minimum, goes right through the 0 right at 0.2 here. I'll show you the problem with this. So the dots here are my colleague's data in a wind tunnel. Now he's using a small ball, it's not a real soccer ball, and it's plastic. And the places where the seams would be tend to be like corners. So it tends to be a little bit rougher. So the drag coefficient tends to be a little bit smaller in some regimes, like in here, but then it gets actually bigger than a real ball because of what happens after you get into a turbulent flow situation. My colleague in Japan, for a 32-panel ball, his drag coefficient data is a function of Reynolds number, which again is just like plotting this as a function of speed here, does the following. And there's this characteristic drag crisis, as we call it. You actually go faster and this drag coefficient drops. And the fun thing about a sport like soccer or baseball is the sport's played where that drag crisis is. That's what makes this so much fun. Well, that range of Reynolds numbers I showed you, I only had one Reynolds number, or one drag coefficient I was assuming for that entire trajectory. I wasn't taking it to be velocity dependent. So that whole range of Reynolds numbers could be here. Well, have we matched the prototype little scale mini balls, or have we actually gone with the real ball? Kind of hard to tell. So they don't have a very large gym. I said, well, let's take the ball launcher, we'll turn it toward the diagonal, we'll try to shoot it as far as we can. We don't want to go too high and hit the rafters, so we try to get the fastest launch speed we could, and we got the next set of data right down in here. So I think we're tracking the real ball more than we are the scale ball with that result. With the lift, we use the first camera. So there's an exponential degradation in the spin as you move along the path. A ball comes off a baseball bat, 2,000 RPMs. By the time that someone catches it, it's under 600 RPM. I mean, if it was going that fast when you tried to catch it, it would roll out of your glove. So there has to be some reduction in the spin just to catch the ball. But here, over this very short time scale, right at that first camera, I am able to track the spin. And we have this thing called the spin parameter. The spin parameter measures the equatorial speed, the r times omega of the ball, divided by its center mass speed. Now, wind tunnels can spin balls, but they can't spin them very fast. And wind tunnels are very limited to how far you can go up in the spin parameter here. And I'll show you some data that illustrates this better, but we're able to extract drag and lift from that first camera. And we can do this for all kinds of different settings of our wheels. So here is wind tunnel data. Wind tunnels only go up to about a spin parameter of 0.3. So again, you want to make spin parameter big, you got to really spin the ball fast, or you got to make the speed really slow while it's spinning, which is also tough in a wind tunnel to just have a light breeze over a ball. It's not very accurate. So most wind tunnels are getting up to about 0.3. Well, I tell my colleague, hey, let's do this outside the wind tunnel, and we can get data out here. Spin parameters 1 or bigger. In fact, what I showed you here, I showed you 4 points here. We match the wind tunnel data with these 2 values here, and we're also able to get values where the wind tunnel doesn't see. We did this with the team guy's ball, And again, the wind tunnels are going to stop about here. We've got lots of data past the spin parameter 0.3 that the wind tunnels are not getting. So we're anxious for the wind tunnels to catch up to us a little bit here, see if we're getting about the same numbers here. The last thing I want to show you here is some dust experiments we did. Now, it's the end of my time there. I'm thinking I'd really like to study this boundary layer. You know, the air comes off of the surface of the ball in really complicated ways, and how are we going to study this? So I thought, well, we could inject some smoke in the wind tunnel, but he doesn't have a very big wind tunnel. It also gets a little bit messy and hard to do. You could do like the Japanese do and get this really highly toxic thing. They got to wear masks and gloves and stuff to put on the ball and shoot it and try to watch it come off. Instead, we just used some chalk. So what I did was I would stand over here next to this like black curtain with a handful of chalk and just clap out some dust. My colleague would drop the ball in there and fire it right into the dust cloud. And then we have another student here, Nick Emerson, who was working our high-speed camera, and just thought, well, let's see what we get. And, you know, we can make a nice little sketch here. My colleague, for some reason, used a volleyball in that picture instead of soccer ball. Oh, we got some beautiful pictures. The great thing about this drag crisis is where the drag is high, the drag coefficient is high, the separation kind of in this laminar region is large. So the separation of that boundary layer happens at a large angle like this. The faster you go, the separation takes place back here, which signals a smaller drag coefficient. So this is a ball moving a little more than 17 miles an hour. This one's almost 43 miles an hour. And we were able to go in with all of these shots that we did, these are non-spinning, and measure these angles. And I had a great time with this because this is where we did our experiments. It was right in here, where the drag crisis is. And the angle that we're going to measure is try to estimate where the separation happens at the top or the bottom. So we measure that angle phi or phi or however you want to say it. This is what we got. And there's one mystery here. Had a student who built a little goniometer out of some cardboard and put some little arrows here that we used to try to estimate, took the ball, the same company model, and found exactly where on here we could match it with the video. And here are the angles. We plot drag coefficient versus speed. On this axis, I'm going to show you the angle of separation. So up around in here, for all these shots at these lower speeds, separation angles are between about 180 and 200 and some odd degrees. That one that I showed you that was moving really fast was down here around 95 or so degrees. And then we saw this pattern where you get past the drag crisis and then this thing would drop. And then it would drop for our real high-speed ones, except for the fact that we have 3 data up here. And this right now remains an open question. And when I presented this at our international conference in 2012, it generates a lot of conversation, but we've yet to resolve this puzzle. I don't know really what was going on. The balls were in different orientations. These were 32 panel balls, so we tried to eliminate the seam orientations. But every shot we fired around that speed had a launch or a separation angle greater than a little bit before and a little bit higher speed. Again, that's one of the great things about doing science. And understanding these balls is critical because if you look at the Jabulani ball, if you're before the drag crisis, that ball had more drag than a team dice ball. So the lower speed balls that were hit by the players, the goalies would notice coming at them a little slower. Once you got past the drag crisis, however, the Jabulani ball went below the team dice ball. So then it was hopping fast. So the goalies had a lot of trouble adjusting to this. So again, I'll add another shameless book club, but the publications on this, if you're just looking for a general read, Physics Today invited me to write a little, what do they call these, quick studies, a little two-page thing in there. So for the World Cup in 2010, and that was probably the most accessible, but that's the gist of those two pieces of research.
I'd love to have some conversation. Let's have power.
So I appreciate your time. Questions? Sir?
Some of the reporters must have asked the Tour de France officials and the team captains and such, hey, you guys are blowing last year's times out of the water. What do you attribute your
Well,
success to? Like,
It's a little harder than that because once you finish the stage with a given time, I mean, every stage is different. So it's not like they're running, you know, the 100 meters and all of a sudden it's Ben Johnson, you know. I mean, it's not like there's this huge gap between last year and this year with exactly the same race. But once you start going back and you look for similar stages, sometimes you got to go back 10 or 15 years to find a stage that looks very similar to what was run in this current Tour de France. And only with that little bit of digging do you start finding out that these speeds are anomalous. Now, once they came in with average speeds that were high, we started to read into that second week that some of the reporters were saying, you know, wow, these speeds seem kind of high, and what's going on here? And of course, you read the message boards and all these other conversation places, and everyone has the same comment. Yeah, I hate to think that that's the explanation.
but none of the tour officials have said, oh, we're doing something.
Not that I know of. Yeah.
During that 10 years of modeling, how much does your model change just for general technological advances, better training, that kind of thing?
We did increase the power slightly from one, say, 2 or 3 year period to the next. We started to notice training's getting a little bit better, athletes are getting better, you know, the cyclist technologies, bicycle technologies through the roof. I mean, some of these bicycles that the Japanese put out this year, I mean, they'll have pictures of these things advertised. You can't even see the bike. I mean, they'll have an end-on view of the bike, and you're looking at this ad, and someone like me on the other side of 40 is like, where is the, oh, there, okay. There's the bicycle. I mean, it's unbelievably thin. I mean, these are incredibly low drag bicycles. But of course, you still have a human being sitting on top of it. I mean, there's only so much drag you're going to be able to reduce just by making the bike two-dimensional. But yeah, I mean, we have had to make incremental changes. You know, one year we kept noticing that we were fast, and we checked the weather, and for 5 or 6, 7 straight stages, they all fought headwinds. And we actually found what we needed to do to improve the modeling by adding in that component. But it feels like a bit of a fudge because we have to do it after the fact. It's like, you know, you tell us what the headwind is, now we go back and make a new prediction, which isn't really a prediction anymore. Yes?
Have you looked at any of the any correlations with the physical characteristics of the contestants in the Tour de France? Height, weight, things of this sort?
Just the basic biographical information you get online about the cyclist, as you say, height and weight, doesn't seem to be that different. I mean, these cyclists are fairly small, I mean, you know, weight-wise. Height, there's a little bit more variation, but I mean, they're compact. I mean, they have to be able to stay on a bicycle for 4 or 5 hours, and, you know, they're burning 7, 8, 9,000 calories a day on some of these stages. It takes, I mean, the training and preparation for this is enormous. I mean, you have to you make up those calories somehow. I mean, you have to do a lot of eating and preparing the night before and the morning of and all this just to be prepared for, okay, over the next 5 hours, I'm going to lose 10,000 calories. That's a lot. Yes?
Have you compared your kind of power inputs to, you can find the power files from a lot of these things posted online?
Oh, yeah. Yeah, these are consistent with what we're seeing.
A lot of people,
They actually wear them now. like a couple of the cyclists this past year wore a device that would try to estimate what their power output
No,
is.
they've got power meters in the bikes now.
Yep.
That records every single kilojoule they do the entire day, and their coaches look at it. And some of them actually make it public, and it's like, that's a good way to see if people really get faster. Because so I was wondering if like the numbers you would find from that had gone up significantly.
I mean, the
last
power
year.
numbers that the people who are putting these things online are consistent with what we're using. Chris Froome did not put his power numbers on. So I don't know what those numbers are for him. I mean, I could go in my model very simply on a blink of an eye and change the power to get whatever time I want to get. And I can see what power output would be needed.
I'm just wondering if the power outputs average from this year were significantly different for all the cyclists compared to last year, or just for like
Well, I mean, to match the times, we would have to crank these up a few percent, which is it's a big change from one year to the next.
Well, so the weather sometimes makes you slower. Have you, so one thing that may change from year to year is what direction will this turn, this angle to the other end. So could it have been that this year the weather helped more than hindered? So that they had more wind in their back, for example? or something like
I've
that?
tried to look back at past races, and it's a good question, because we have tried to look at weather trends. You go back 10 years or more, it's really hard to find really detailed, this is what the wind was doing this day, it's in this direction, it's this speed, in this part of the stage, they were battling in the other direction or whatever. We've been taking better notes the last couple of races, 3 years races, to notice what the wind direction's doing during a given stage. I mean, so much of that stuff changes too when you're winding around these different roads, and we were talking earlier with somebody, I mean, you got fans crowding around these people. I mean, sometimes they get shielded from when, the flags that people are holding up.
That's kind of towards the end. And
Yeah.
In the head stages, so I mean, most of the time.
I haven't found a consistent pattern where I would say, this year they're all getting tailwinds or something, helped by the weather. I mean, some of those stages were pretty severe tailwinds. They were even outperforming us.
So basically, what you seem to be hinting at is that maybe there is a super duper type of enhancement, drug enhancement, or something, a new way.
I mean,
that they're-
something happened between 2012 and 2013 that, I'm pleading my own ignorance. I mean, either there's some technological advancement in the way you can more efficiently transfer power from the cyclist to the bicycle, something in the training that I just can't find in the literature. And if it's out there, I welcome hearing about it, yeah.
So some of the advances that occurred in bicycle is they've gone to actually bigger tires, which has increased the, I'm not a physics person by any means, but it's increased they've looked at race cars and things like that, so they've actually increased the tire
Footprint
size
on that.
for traction, increased traction. They've actually built suspension systems in the back of bikes so that the tires aren't bouncing. So that's a big.
And I know the gear shifting is now more automatic than it used to be.
The other thing,
Electronic gear
the
shifts.
flat stages, they're all wearing, all the bike companies now have wind tunnels, Specialized actually have their own wind tunnel now. They're all wearing, on flat stages, aerodynamic helmets.
I mean, they were doing that last year too, so.
It has to be a change that happened from
And
one year to
the other thing that I don't understand enough about physics, but one of the things is the makeup of teams have changed. So on the flat stages, there are flat teams now on the tour. So
Oh yeah, I mean, the
Marcel
strategy is
Kittle's-
a huge part of this.
Marcel Kittle's team is all these powerful big German guys who keep going really fast on flats. And they don't care about the mountains. And then Froome's team is all about these little guys who have really great power weight ratios. And they're going up at means that you can never.
Sure. And you're, taking your chances, or do you want to win all the flat stages, do you win all the mountain
The
stages?
confluence of little factors that add up to the theory there.
I mean, it's all under consideration, it's just trying to find that one thing that seems to make the jump as large as it is. Yes, ma'am?
I'm gonna ask a question about soccer ball. I was just curious, like, do they have a particular goal in mind in terms of like, are
They
they
want
trying
the
to
ball
make
to
it a
go in the
higher?
goal.
Well, no. I mean, the designers of the ball, like, do they want more drag or more lift, or like, I mean,
Well,
like, what is the goal?
I mean,
of
when
achieving
Adidas
this
makes
every
the ball, and a lot of the research is done, or the testing done along with it over in the UK, the idea is to create something that isn't going to be that noticeably different from what the players are used to. You don't want to just roll this ball out for the game's biggest stage, the World Cup, and then all of a sudden everyone's complaining because, I kick it and it starts looping around my head. You don't want something so dramatically different from what they're used to. I mean, still want the game to be played at the high level, and their reaction times are going to be based on, having played with a ball of a certain type. And that was the problem with the Javelani ball, is that, those low-speed kicks just didn't have they had more drag, and the high-speed kicks had less drag. So, of course, in South Africa, half the games are played at sea level, and the other half are at mile elevations. That had a big influence on the final match, too. But the goalies were noticing, wow, this ball's really fast. And that's, because these people who were shooting from 10 or 20 yards out and just really, really hitting it hard, I mean, that was in a low drag region compared to previous balls they used. So, I mean, to my understanding is that they're not trying to create something that's especially controversial. I mean, they want to be able to have the sport played at an elite level that the players are going to like. I can't imagine they're sitting there thinking, gosh, put these little dimples here, then the goalies will never stop it.
But there could be unintended consequences that I may favor some teams versus others because they're different styles of play.
Sure, and the aerodynamics comes in, of course, during the shots, and if you're the Spanish team, that they're just all about passing, and it's incredibly beautiful to watch that passing. But a lot of that's happening, the ball rolling on the grass or kind of low off the turf or something. But even then, when you've got longer passes, the aerodynamics play a role. If your ball has got more drag than you're used to. Now, someone like me who's never played soccer on a organized team or anything like that, more than just kicking the ball around, I'm not going to notice the difference between a Javelani ball and a team guy's ball. At that level, those little subtle differences will be noticed, and the players did notice them. It's true in any sport. The elite, the best of the best, are going to notice those tiny differences.
How different are the values from just like the canonical value of drag and the sphere that you see in like the floating type of how, like, are they
Well,
standard, or
the picture that I may have this graph somewhere, but I have to go looking through my files to find it. So if the ball is completely smooth, then this transition would happen out here. If this was a golf ball, the transition would happen earlier. So the rougher you have the ball, the sooner that transition happens. What happened with Javelani is it started up here, and then it transitioned down like this and went lower than the ball they used in the previous World Cup. Yeah, last question?
What are the ranges that elite level soccer players can actually shoot a soccer ball? I don't actually know is that 0 to 40 relevant, or do they go?
Some of the longest, this isn't just goal shooting. Some of the goalies who will, kick the ball 2/3 of the way down or something, those things can be 60, 70 miles an hour. And they're really hard hit balls. Put this up a mile high elevation in South Africa, and you're going to get top speed. Now, one thing about higher elevation and less air resistance is you also get less lift. And you can throw the ball harder in Coors Field, you just don't get quite the same drop from your curveball. So, I mean, it's got a little bit of a trade, but, I mean, yeah, the speeds are quite large there.
I might be missing something, but why do you, if you've got these random variables, these unknowns like wind velocity, I'm sure that oxygen density also makes a difference, therefore temperature makes a difference. Thinking about the tour. Why do you not just publish a confidence interval and factor all these things in? Or do you?
No, I mean, the thing is, it's a really complicated problem. And we're simply trying to get our foot in the door of how do we model it, how can we predict the winner of the Tour de France, given stage 1 through 21, let's say. So we were not privy to all the strategies that were going to be employed. We don't know when the peloton is going to break up. We don't know when people are going to leave the peloton and start chasing. Who's going to try to start early. We don't know when crashes are going to happen. And there's so many factors. It's such a complicated problem, and the terrain and everything. I mean, this is a reasonable start, and we're still pegging these things to within a few percent. So,
But weather seems to be something that is, you could assume a fairly reasonable distribution for it. Put that in there and give us a plus or minus.
oh, sure, yeah. I mean, and we've thought about doing that. Like, say, you know, suppose the. In fact, I had I know last question was called, but I'll just go back real quick to the. Can't remember if I had that written on there, but the effect of wind on. Which one was it? This one right here. Each 1 kilometer per hour of a headwind grows our prediction between 7 and 8 minutes on the stage. So we figured there was an average of a 3 kilometer headwind because we were 18 minutes off. So I mean, we know what a headwind's going to do on average. So we could certainly say if the wind's averaging between -3 and 3 kilometers per hour, expect the time in this range. I think we're a little more trying to get a specific number pegged. I mean, it's just part of the fun. It's just part of the fun of doing it a day in advance.
Okay, let's thank Professor Goff.